Hello. Here I'll talk about the Galois group, the symmetry group of a special quartic, of a bi-quadratic. A general shape of a monic such is t to the 4 plus some coefficient times square variable plus some other coefficient. So as usual, let's call the base field some letter k. Yeah, the first ingredient in analysis of the Galois group of such polynomial will be its resultant cubic, which if we compute it, it will have the coefficients c for t squared, negative 4e for t, and then positive 4ce as a free term. And it is not hard to see that such factorizes always into the linear term t minus c and then the quadratic t squared minus 4e. So we could see when it factorizes further, that is even only if e is a square in our field of coefficients. So we immediately have some partial answers. Let me start building the table of answers. So I'll look at the Galois of the polynomial and then the Galois of its associated resultant cubic, and then what I'm really after is a nice convenient criterion in terms of coefficients. So what I know is the associated resultant cubic always factorizes at least into two terms. So the group of symmetries could be C2 permitting two square roots of this if they're not in K, or if this E is a square, then all roots are in K and then the symmetry group is a trivial. So that is easily dismissed, or rather determined by the condition that E is a square inside my coefficient field. In that case, it corresponds to the symmetry group V4. And these two other cases which I separated will correspond to cyclic group or non-abelian dihedral group. So in both cases, E is not a square. And to distinguish between them, to see the distinction in terms of the coefficients, we will have to do some modest analysis. So let me perhaps fix the names for the roots, just write it compactly, grouping them in pairs, plus and minus. I will be just running from 1 to 2. So the squares are roots of the associated quadratic, and then the actual roots of the polynomial f are plus and minus y's. Now let me call this set of roots x, and then the elements will be y1, negative y1, y2, negative y2. So the analysis I'm going to do is to really list these groups, these possibilities, as the groups of permutations of the roots, and see how can I distinguish between the two cases here. So obviously, if I have a permutation, let me look at the symmetric group on these roots and then put some condition which is inevitable due to the special shape of the polynomial. So I will be looking at the permutations which will have the property that they commute with minus, with negation. Negative, the value on the negative of the root is the same as the value on the root with the negative sign. That is inevitable if we look at an automorphism. Negative sign is an element of the ground field, so it is transparent to our symmetries. So let's see what the elements in this group are. Let's list them. And to see what they are, I will write them in permutation notations as products of independent cycles on my permuted elements. But to see what they are, it's enough to determine them on just their values on two elements, y1 and y2. If I know what happens with my permutation on y1 and y2, I know it everywhere. I know what happens with negative y1. It just goes to the negative of the image on y1, and so on. So I will just have to list all possibilities. So I will start with the identity. That will be corresponding to the identity permutation. What else could I do? Well, I can still fix y1 and then flip y2. And vice versa, I could flip y1 and fix y2. I could flip them both. I could still satisfy these conditions, right? I could now start and moving them around outside of their pairs, so like y1 goes to y2, and y2 could go to y1 back. Or y1 goes to y2, but y2 goes into negative y1. That's all I could have if I know where y1 goes. There are only two possibilities left. You could see that you cannot go with y2 to y2 or negative y2. It will break in invertibility property. And then I could do the same. So what I did, I just sent a root into another root and then flip the sign for the second option, and now I could just do y1, and negative y2, and then negative y2. So this is, I claim, a complete table of possibilities. Nothing else could happen. And the conditions are that we're permuting for things, and we're permuting them such that a negative sign is preserved. So this is a list of 8 possibilities. Identity is the first. The second is in cyclic notation, using this as labels for the set. I have y1 fixed, so I won't list it in my cyclic notation. y2 is moved into negative y2, so I have a transposition on this pair. This is the choice. Alternatively, I could have this choice, a transposition on y1, negative y1. Then I have a pair of transpositions, y1 flipped with its negative version, and simultaneously y2 and y2 negative are interchanged. So that is this column. This column, well, let me start new line. This column says that y1 goes to y2 and y2 goes back to y1. And what happens with negative y1 is determined by the property it goes to the negative y2. So I have another pair of transpositions, and then where am I? I'm here, and then I have this possibility which starts with y1 goes to y2, y2 goes to negative y1, so I'm not closing the cycle, negative y1, it goes to negative y2, and then negative y2 goes to positive y1, and I'm closing the cycle finally. So that is this column starts still with y1, then goes to negative y2 goes to negative y1 goes to positive y2, and y2 goes to positive y1, so I'm closing the cycle. This is one before the last column. The very last column interchanges y1 with negative y2, negative y2 goes to negative y1, so I'm closing the cycle, and negative y1 goes to positive y2. So I have my last pair of transpositions, and I have a complete list of elements of a dihedral group inside my symmetry group. So this is, if I have all my symmetries, all my allowed symmetries, I'm in this case. But yeah, I want to see what is the distinction between this and that. So what is the case when I have only a cyclic group of order 4? Well, let's look at possible elements. We have two elements of order 4, and they are cubes of each other. And then the square will be y1 goes to negative y1, y2 goes to negative y2. So it will be this pair of transpositions. So this, and this together will give me my cyclic group. If I call this permutation, which corresponds to this column, right? So if I call it tau, then this column, y1 goes to y2, y2 goes to negative y1, and that is it. So this four cycle will generate a cyclic group of order 4. So I'm interested in seeing something special about the case when the symmetries are just fourfold. And here's a trick. Let's look at the combination of roots. The product of them, and then the product with the difference of squares. So that is an element in, say, splitting algebra or in the splitting field of the polynomial. But in the case when the splitting field has this symmetry group, I could see what happens with this element under my symmetries. So I have 4 symmetries, but they're all powers of tau of this one. And I will have just one computation done. I will do this tau to the element and see what this permutation does to the expression. Well, y1 goes to y2. So instead of y1, I'll have y2. y2 goes to negative y1. And then inside the difference of squares, y1 goes to y2. So I have y2 squared instead of this. And then with negative sign, I have y2 replaced by what it should be, by negative y1, so negative y1 all squared. And if you look at it, yeah, we'll have a negative sign in front of the whole thing, but then we'll have a negative sign because the order flipped. So if we rewrite it, we will see the original element. So tau fixes this element. The whole group C4 fixes this element if the group C4, if the Galois group of F is just a cyclic group generated by the 4 cycle, then this element is fixed inside the splitting field, and hence it should be a coefficient. And vice versa, it only happens when the group of symmetries is just a cyclic group of the 4 cycle, because if we say take any of those transpositions, like the first one, call it nu, and see what happens with our element under this transposition. If we're not cyclic group C4, then the only larger group we could have is the whole group. So we will have nu in it, and what nu does to our specially chosen element is the following. y1 is fixed. Nu doesn't change y1. y2 flips the sign, and the difference of squares doesn't change because of that special shape of the symmetry. And so the overall effect of the symmetry on our element is negative sign in front. The element changes. So this condition that this element is a scalar in the base field is equivalent to the condition that the symmetry group is exactly C4. And so we have a characterization of this case, and hence a distinction between these two cases. This element has to be an element in K. How can we link it with coefficients? Well, let's take the square of this element. So the square of this times the square of the difference of squares of y's. After all, y's are roots of the quadratic polynomial t squared plus ct plus e. So that squared is the discriminant of this quadratic polynomial. It will be c squared minus 4e. This is the product of squares. Maybe I will write it as the product of squares. And the product of squares is a product of the roots of that quadratic, and that is just e. So what I'm saying is that my symmetry group is C4, my Galois group is C4, if and only if this element, or rather this element squared, this element is inside K, but this element squared is this quantity. So I'm saying that this quantity is a square, non-zero one. So that is a complete characterization of the special case when the group of symmetries is cyclic. And that is a convenient criterion in terms of the coefficients of my bi-quadratic. So to be cyclic, I should have this quantity to be a square, and otherwise, when it is not, so this is c squared minus 4e. If it is not a square in my ground field, I should have the maximal allowed symmetry group, the diahedral group D4. So that's a full analysis of the case of a special quartic, bi-quadratic quartic. See you later. Goodbye.